Good evening, everyone. So we are very pleased to have Pedro Ribeiro from University of Porto, Portugal, to give our next talk in Special Functions and Number Theory seminar. So Pedro is currently a PhD student working with Professor Semyon Yakubovic at University of Porto, and he works in analytic number theory. Today he'll be talking on some generalizations of Ramanujan, some formulas of Ramanujan in the spirit of Koshlyakov. Over to you, Pedro.
Thank you so much for the nice introduction and for the invitation. Let me just share my presentation. I think this is the one. Okay, yeah. This is in the middle, sorry. Okay, all right. We move to the beginning. Okay. Can you see the beginning of the... Okay, the title? Okay. So, as Professor Dixit said, I'm going to present the generalizations of some formulas in the spirit of Koshlyakov. First, I'm going to actually repeat some parts of a talk given by Rajat Gupta here in this seminar. Just mentioning briefly the tragic story behind Koshlyakov's memoir, which inspired this work. Then give some basic facts about Riemann zeta functions, as to some members of the audience cannot be so familiarized with that. So I'm going just to give some basic things about Riemann zeta function, how Koshlyakov zeta function generalizes Riemann zeta function. Then I will mention the paper by Atul Dixit and Rajat Gupta, which actually, when they presented on OPSFA 2022, the 16th OPSFA was the first time when I heard about this theory. Then the question that motivated this work, epsilon zeta functions in Koshlyakov theory, and then to present the generalization of the Ramanujan's formula in the spirit of Koshlyakov. So let me just mentioning some basic things about Koshlyakov. Perhaps all of you know. Koshlyakov was an outstanding Russian mathematician. One of the most famous results due to him is this formula, this beautiful formula, which involves the modified Bessel function of the second kind and divisor function. Is not actually, it was attributed to him from a paper of 1929, but actually was later discovered that Ramanujan already had this formula in the Lost Notebook. But nonetheless, this is known as, even nowadays, as Koshlyakov formula. This is one of his most famous results. Here, alpha and beta are such that alpha beta equals pi squared, and gamma is the Euler's constant. Okay, so he was a student in the University of St. Petersburg in the time when it was called St. Petersburg already, before the Russian Revolution. He was very interested in the work of Voronoi, and it was through Voronoi's work that he established that formula that I mentioned in the previous slide. Then he moved to Crimea. After 6 years, he moved again to St. Petersburg, now called Leningrad, due to the Russian Revolution, and stayed there. He had a tremendous success during these first years in Leningrad, publishing several papers on summation formulas mainly, and he caught the attention of Godfrey Harold Hardy by electing him as a foreign member of the London Mathematical Society. Hardy was very interested in the work of Koshlyakov at this time. They worked in similar areas, like Hardy also worked a lot on Voronoi summation formula, on analogs involving the sum of square functions, of two squares function, and Koshlyakov's work was very similar in this line. Okay, but like many mathematicians before him, and at the same time as him, in the 20th century Russia, Koshlyakov's life met tragedy, like Luzin and Egorov before him, Egorov for religious reasons, Luzin for political reasons. Koshlyakov also faced some setbacks in his career due to historical context. And as you know, on June 22, 1941, the Molotov-Ribbentrop Pact between Nazi Germany and the Soviet Union was violated by Hitler. Okay, and so the German army started to move towards the Soviet Union. And the German armies, of course, held a psychological superiority due to the blitzkrieg, due to the lightning fast victories that they got in the east. As you can see, I mean, the distance between the German border and Leningrad was like 720 kilometers. And by September 8th, they already reached Leningrad. So it was not actually a siege, it was a blockade, because the Germans could not circulate the whole city. They left an area in Lake Ladoga that they could not control. And this is crucial in the next story. Okay, this is the thing. The Germans held a strip of land ending at the point where the river Neva leaves Lake Ladoga. Consequently, the only connection of Leningrad to the rest of the Soviet Union was by boat across Lake Ladoga or on truck over the ice in the winter. So the truck with the supplies could only reach Leningrad through the ice in the winter. So the conditions were very, very, very harsh. 3 million before the war lived at Leningrad. The population shrunk to 700,000 to 800,000 in the summer of 1942. In the winter, in the first winter of the siege of the blockade, which was the coldest of the century, the air reached something like minus 34 degrees Celsius. More than 4,000 people died every day. So the conditions were very, very, very complicated at those times. In this blockade, the bloodiest blockade in history. And actually, Hitler planned to raise the city to the ground. Hitler, like Rome did with Carthage, for instance, Hitler wanted to just eliminate the city and relocate the population south. So there was no chance that they would leave Leningrad soon. They kept them. The Germans, the goal of Hitler was to raise the city to the ground. So the Germans kept them there until they could not no more. Like the siege lasted for 872 days, a long time for a siege, and it was very complicated. At least 850,000 to 950,000 died of starvation, and it's estimated that around 1.1 to 1.5 million died during the whole blockade. Some stories estimate that during the siege, people ate 300 calories a day. This you can have an estimate of how much is this. This is like 300 grams of bread per day. But for workers, I mean, workers with manual workers. But for office employees, including scientists, they were granted 150 grams of bread per day. The starvation was immense. The cold was immense. The bombings, like the Luftwaffe was keeping bombing the city, trying to kill people and to eliminate strategic offices and the strategic buildings, and also bombed the ice on the lake where the trucks were carrying the supplies. So yes, the conditions were very, very complicated. Some of the scientists and some of strategic industries were evacuated in July, 2 months before the Germans reached the city. For instance, Sergei Bernstein, the well-known, was evacuated at the beginning, and Krylov. But most of the scientists were kept in Leningrad, including Koshlyakov. And at this time, like the siege was going to last, the NKVD is like the People's Commissariat for Internal Affairs, then intervened and started to interrogate scientists about their commitment to the German cause, like if they were traitors or were trying to bring the Germans to the city. And yes, and Koshlyakov eventually was caught in this set of accusations. Like this, the first accusations of the NKVD was Ignatovsky, who worked as a spy during First World War. But through Ignatovsky case, he denounced the colleague Strakovich, and then Strakovich denounced a whole bunch of colleagues in Leningrad because he was tortured, he was starved, and he started to denounce several colleagues. And Koshlyakov was implied in this first in this torture and this and he denounced Koshlyakov. I mean, denunciation by denunciation, by May 1942, it reached 127 scientists. Most of them died in jail. A group of 13 mathematicians, the Rose-Korslyakov case, were accused in the early investigations. Rose was the dean of the mathematics and mechanics faculty and counter-admiral of the Soviet Navy. So Korslyakov was implied in this case. They were interrogated. They were starved during the interrogations. Forced to stand for hours was another form of torture. And eventually it was humanly understandable that an offer of a bowl of soup was enough to force them to sign a confession. Like, they were starving at the beginning of the war, then they were accused, then they were in jail, then they were starved again, and of course they would write whatever the NKVD wanted to write. And Korslyakov actually signed something of the form. I intended to establish relations with the German commander. I would like to atone for my guilt by participating in our working front. In particular, I'll be very happy to complete my work on summation formulas, which I have been conducting for several years. So we actually admitted that, of course, it's a forced signature. It's not true, but it was so it was suffering so much that he eventually ended up signing this confession. First, Korslyakov and his colleagues were sentenced to death, but some days later, the accusation was replaced by 10 years of imprisonment and hard labor. So it's here where the story of the manuscript begins. This is taken from the talk by Rajat Gupta, which is taken from by this memorial publication. On the grounds of complete exhaustion and complicated pellagra, Korslyakov was classified in the camp as invalid, was not sent to do any of the usual jobs. The opportunity to return to scientific work had a great influence on his general health and frame of mind. In fact, as he himself says, this was very difficult as he did not have many of the books he needed, and because of the very serious shortage of paper. He was forced to carry out calculation on a piece of plywood, periodically scraping off what he had written with a piece of glass. So how could he manage to do scientific work in these conditions is outstanding. And after all these problems during the siege of Leningrad and the starvation and the cold, how was that possible? I mean, it's amazing how we could carry out the work in prison, in the Urals, in the mountains, exhausted and with disease. So I'm going just to give some details of the work. Korslyakov wrote 2 long memoirs. I'm going to talk about one of them. He sent then the memoir for the examination to Steklov Institute of Mathematics, in which Vinogradov was then the editor. They recommended, of course, its publication because the content of the manuscript seemed so powerful to Sergei Bernstein, who was then assigned to the paper. So this is the end. Actually, the sentence by Korslyakov was then repealed. Actually, he was one of the scientists that had the best or one of the better end of the stories. And most of them died in the camps or in jail, or were assassinated after. His sentence was repealed in 1951, and he could continue to work on applied problems and in pure mathematics after the World War II ended. So I'm going to in this presentation I'm going to focus on this paper, a study of a class of transcendental functions by the generalized Riemann equation. So just a brief introduction to the Riemann zeta function. The Riemann zeta function is defined by this Dirichlet series, which converges absolutely when S, or real part of S, is greater than 1, and diverges, of course, when is in another part of the plane. It's actually well known this identity was one of the first problems regarding Riemann zeta function, the Basel problem, and was solved by Euler. One of the open problems was opened by almost 100 years until Euler solved it. It is also known by Euler that the Riemann zeta function can be at even integers as this expression, and a rational multiple of a power of pi, where these rational multiples are belonging to this generating function. And after Euler's contributions, Riemann arrived in 1859 and actually was the first mathematician seeing this function as a complex function and applying the machinery of complex analysis to study this function. And one of the starting points by Riemann was this integral representation. And when the operations are allowed, which is in the region of the absolute convergence, this integral representation was the enough step for Riemann to derive the analytic continuation, because now this integral, although it makes sense only in this region, real part of s greater than 1 can deform the path of integration in such a way that this formula will remain valid for every s. And from that, it could derive all the analytic properties that the Riemann zeta function have. So this integral representation is essential in Korsakov's work. Korsakov's work is actually, mutatis mutandis, the work of Riemann, but this function here, 1 over e to the x minus 1, is replaced by a more generalized function, as I'm going to briefly explain later. So some basic properties of the Riemann zeta function. It is analytic everywhere except at a simple pole located at s equals 1. It has this meromorphic expansion, where gamma by definition is given by this. It has simple zeros located at the negative even integers, and it satisfies this functional equation, like the reflection formula in which the invariant subspace is the critical line, is the line real part of s equals 1/2. Okay, and this is a crucial point in Korsakov's theory, like this reflection formula. And it was not known by Riemann. It was only known, although Riemann had already the modular relation that codifies this. It was not even known to Arri when he proved the infinitude of zeros at the critical line, but actually this functional equation characterizes the Riemann zeta function. This is a theorem known to Hamburger, 1921, which says that if we have general Dirichlet series of this form, which are absolutely convergent in some region of the complex plane, then if they satisfy a functional equation of this type, then they must be a complex multiple of the Riemann zeta function. Of course, there are variants of this. The most known variant is due to Ecke, which used the theory of modular forms, but as the additional condition that Fs and Gs must have a simple pole, not a general continuation, as this assumes, as Hamburger's theorem assumes, but the functional equation is more general, is more like Ecke functional equation. There are, of course, other variants again, when n and n here are replaced by general sequences, but there are some restraints on the n, like to be positive. But yes, this is one of the motivations to introduce Korsakov's zeta function, is this uniqueness of the functional equation. One can also see if GS is not a Dirichlet series, how can we give an example of something that satisfies this functional equation with G not being a Dirichlet series? And that's precisely what Korsakoff did. Like we have a functional equation like this F is a Dirichlet series, but G is not. Korsakoff gave the first explicit example of that. And now I'm going to introduce the Korsakoff zeta function. It started with the first Dirichlet series given by this, where lambda n are the sequence defined by this. For each p, we can assign a sequence lambda n for which this transcendental equation is solved. And you construct this Dirichlet series. One can see that lambda n, the solution of this transcendental equation, is also always between n minus 1/2 and n. And from this comparison criterion, one can see that this converges absolutely in this region, the real part of s greater than 1. In the limiting case, like when we take p to the infinity or p to the 0 tends to 0, one can easily check that the sequences, the solutions of this equation, are respectively the integers n and the alpha integer n minus 1/2. And one can see then that in this limiting case, zeta p tends to this function, zeta s, and to the s minus 1 zeta s. So one can retrieve the theory of the Riemann zeta function by looking at this generalized Riemann zeta function known as Korsakoff zeta function. But as I told you, this will satisfy a functional equation with G not being a Dirichlet series. F is already a Dirichlet series, of course, zeta p is a Dirichlet series, but V will not. And next, Korsakoff introduces another zeta function, which is now not a Dirichlet series because there is this dependence on S in the numerator. This S2 pi pkk is actually a combination of incomplete gamma functions or Whittaker functions. But one can see easily that if p tends to infinity, formally one can see that this tends to 1, right? P infinity. Yeah. Formally, interchanging the limits, it's one can see that this tends to 1. And then we get 1 over gamma times the integral of gamma, which is gamma. X s minus 1 e to the minus x dx. They cancel out. We get a 1. So we get, in the limiting case p to the infinity, we get, again, the Riemann-Zeta function. And in the case where p tends to 0, we get a variant, 2 to the power 1 minus s minus 1 zeta s. So again, we have generalizations of the Riemann-Zeta function and not a variant like Dirichlet error function. These Korsakoff zeta function are related by this functional equation, the functional equation of the Riemann-Zeta function. And then the Korsakoff manuscript is always divided in 2 parts of the form. Like one chapter is dedicated to the theory related to zeta p, and then the next to eta p. Then Poisson summation formula, the theory related with zeta p, and then next chapter with eta p. Always like that, always this duality. Korsakoff also introduced other analogs in this setting. For example, analogs of the Bernoulli numbers and polynomials, generalized Euler-Macroni constants, generalized Jacobi theta function, to generalization of the Hurwitz zeta function, meaningful analogs of the Poisson summation formula, etc. In fact, let me return to Riemann's work. As I said, this integral representation was essential in Riemann's work to deduce the functional equation from the Riemann zeta function. And actually, the importance here is on this fraction, 1 to the e to the x minus 1. And in Korsakoff's spirit, this has 2 generalizations. The first of them is this one. As you can see, as p tends to infinity, this will be the geometric series, which reduces in the end to 1 over e to the x minus 1. And another one, like this generalization, sigma p star x, 1 over sigma x e to the x minus 1, where sigma, by definition, is given by this. So when p tends to infinity, this tends to 1. Sigma of t tends to 1. So this will reduce to 1 over e to the x minus 1. So it's like with these 2 analogs of this function, 1 to the e to the x minus 1, one can work the theory of the Korsakoff zeta function. Okay? Again, we have these representations, like this acts as analogs of this, of the Riemann zeta function. Now we have for zeta p, the first representation of, and for eta p, this representation. Again, as in case of Euler's formula for zeta of the even integers, we have in Korsakoff's theory an analog of this form, where now the generalized Bernoulli numbers enter in the picture. When m equals 1, for instance, we get this generalized basal identity, which when p tends to infinity, it reduces to the well-known formula due to Euler. So yeah, we have like the Riemann zeta function using this kind of integral representations. We have an analog of Euler's Macroni constant in the lower end expansion, which is given by this CP1, given by this limit. As you can see, when p tends to infinity, this reduces to this. For eta p, we have the same thing. We have an analytic continuation with a simple pole located at s equals 1, and whose residue is given by this. In this case, the constant term in the Laurent expansion is a bit different, but one can see that it also reduces to Euler's constant gamma when p tends to infinity, this CP2 here. This Q is the incomplete gamma function. And yes, we have this great theory, and using this continuation of these functions, one can start to build the theory of summation formula and start to deduce new analogs of summation formulas. That's what Korsakoff actually did with some formulas of Ramanujan, which involve integral representations, and the formula of Hardy as well, from 1915. But yes, we can do this kind of things now with this continuation. Just a brief mention, Korsakoff also introduced analogs of the Hurwitz zeta function. One of them, this is the second of them, is explicitly given by this. Okay, as one can see, when p tends to infinity, this will again reduce to the Hurwitz-Zeta function, classical Hurwitz-Zeta function, and he actually proved that it satisfies this equation, like the Hurwitz-Zeta function does. When p tends to infinity, this will reduce to the not functional equation, but the reflection formula for the Hurwitz-Zeta function. I just mentioning here, not the other analog, because this I will mention a result involving a formula for this. It's a PSA. That's why I'm just mentioning this in this slide. Okay. Now let me briefly mention how I discovered this work. It was during a presentation given by Rajat Gupta at OPSFA 16, 2022. I did not know much about Koshliakov's work besides the formula involving the divisor function. And when I saw the presentation, I was immediately interested in seeing the paper and in the kind of the results. As I can read, Atul Dixit and Rajat Gupta are the first mathematician of our century to have studied and extended Koshliakov's work in new directions. For the story of how the manuscript was discovered by Dixit during his PhD years, we strongly recommend Gupta's seminar given in this seminar. So let me just mention one of the formulas that they obtained in their paper, which was a generalization of Ramanujan's formula for zeta in the odd integers. They actually also obtained a generalization of some infinite sum of the gamma functions, another modular relation by Ramanujan. But I'm just mentioning the generalization of Ramanujan's formula for zeta to n plus 1. Which is this, I mean, a quasi-modular relation. It would be a modular relation if somehow this minus beta was a beta and these terms were not appearing. But they generalized this formula by replacing n by the sequence of Koshliakov, lambda n, and by replacing these Bernoulli numbers by the generalized Bernoulli numbers that I showed at the beginning. So they obtained their theorem. Like we have the sequence again that satisfies this transcendental equation. We have the Koshliakov zeta function. We have definition of the Bernoulli numbers in Koshliakov setting, and then we have this very nice formula that, of course, generalizes the Ramanujan's classical formula that is in the second notebook involving zeta to n plus 1. Again, since zeta p reduces to the Riemann zeta function when p tends to infinity, of course, this will reduce to Ramanujan's formula when p tends to infinity. And when p tends to 0, they obtain a new formula. That's why this is kind of nice to work with Koshliakov theory, because although in some limiting case you can get a known result, when you get the other limiting case, you might get new formulas. And of course, this was now how I discovered how I came to know this work, this amazing work. So here I see this. Prior to June 2022, I knew very little about the work of Koshliakov, and at that time I was only interested in one of his papers about Portnoy's formula. At that time, the work for my PhD revolved around the general formalism for Epstein zeta function. When I learned about Dixit and Gupta's work at the conference, I was immediately attracted by the question: is there a place in this theory for Epstein zeta functions? Like, can we use the formalism of Koshliakov's theory, like he did with the zeta functions, to construct new analogs of the Epstein zeta function? And of course, let me just introduce what an Epstein zeta function is. It's like a two-dimensional analog of the Riemann zeta function. Like the Riemann zeta function is just a summation over one variable. The Epstein zeta function is a summation over two variables. But now the M is replaced by a quadratic form, a positive definite quadratic form. We take a quadratic form, am squared plus bmn plus cn squared, in such a way that it is positive definite, and you take this Dirichlet series. It converges absolutely when the real part of S is greater than 1, and it has some properties that are very similar to the Riemann zeta function. It is analytic everywhere, except at the point located at S equals 1, and its residual depends only on the discriminant of the quadratic form here. So one may guess, okay, I have this generalized, I have this Epstein zeta function. How would that work in Koshliakov setting? I mean, it might just substitute m by lambda m and n by lambda n, say, and put the other terms p squared plus lambda n squared, etc., instead of this one. Perhaps that would work, but at that time I was not sure. I conjectured that. But let me see how formally this could work. Just to not to complicate too much with a general quadratic form, let me just restrict to the case when b equals 0, like the quadratic form is diagonal, is of the form m squared plus cn squared, just for to be easier to write the formulas. Consider this particular case of the epsilon zeta function. 1 over m squared plus cn squared. This is still the classical case. Again, we can check this. It is analytic everywhere except at s equals 1. Its residue is like pi over square root of c. It is now the discriminant of this. And moreover, it has also a functional equation. I'm not going to mention it here. But moreover, this is important for the work. It has a meromorphic expansion around this simple pole of this form. This is known as Kronecker's first limit formula. I did not write it in terms of the logarithm of Dedekind's at a function, because I want in this way, it will be easier to get this expression now, and then to see how it can be generalized in Korsakoff setting. So we have this, like this pi over square root of c, which is the residue, and then you have this constant term, which involves this infinite series involving this function that I mentioned before can be generalized in Korsakoff setting. So that's it. So one can conjecture, of course, let me check, 1 over m squared plus cn squared. Okay, that's the classical epsilon zeta function. One may conjecture that in Korsakoff theory, this epsilon zeta function would assume this form. Like, it's natural, no? I mean, I'm replacing m by lambda m, say, n by lambda n prime. It does not need to be attached to the same p as lambda m is. And I'm now attaching these things that appear naturally in the definition of Korsakoff zeta function. P squared plus lambda n squared, p plus 1 over pi plus lambda n squared. This is attached to lambda. Actually, there's a typo here, sorry. This should be a lambda m. Lambda m, lambda m. This is attached to this, and this p prime is attached to lambda n prime. So it should be, I mean, I could declare this as an epsilon zeta function and try to seek analogs of this pole and analogs of this expansion, for instance. But yeah, that was the first guess concerning this. But when we were studying, me and Professor Jakubowicz were studying this kind of generalized epsilon zeta function, we were attracted to which kind of modular relations one can deduce using this generalized epsilon zeta function. And now let me introduce 3 modular relations with Ramanujan that are somehow related with this generalized epsilon zeta function. The first of them is a modular relation, not a modular relation, of course, a summation form which involves the zeta function at 1/2. It is stated in the second notebook, and it is given by this. There are several analogs of this. There are character analogs. There are analogs involving the Hurwitz zeta function. There are analogs where 1/2 is replaced by a rational number, say. But this is the striking, like we have a very simple function here, and then we have this combination of hyperbolic cosines and cosines. It's a very nice formula. So the first step was to deduce an analog of this in Korsakoff setting. And then, let me mention another, a formula that Ramanujan recorded in his lost notebook, which involves this reflection formula, equivalent to the transformation formula for the logarithm of the Dedekind's eta function. And then another one, which is Korsakoff's formula. We have this striking relation that I mentioned in the first slide, often beta equals to pi squared, and we have this striking modular relation. So these are 3 entries in Ramanujan's notebooks that we are seeking to generalize in Korsakoff setting. So the first one is a generalization of this formula here, which is a bit complicated due to the p's that appear, but assume that lambda n and lambda n prime are solutions of these transcendental equations, like in Korsakoff setting. And take sigma t and sigma prime t as these functions, elementary functions in the Korsakoff theory. For p prime, I define sigma prime t as p prime plus t over p prime minus t. Okay, then define, this is a bit complicated, GPA as a ratio of these two functions, depending on p and a greater than 0. Then you have that this formula holds, like p squared plus lambda n squared, this part here coming from Korsakoff theory, this part here that generalized this part here of Ramanujan, 1 over e to n squared x minus 1, equals to this thing. Here appears the central value of zeta, of the Korsakoff zeta function at 1/2. And this is the generalization. Of course, this GP here is a ratio of these two functions. But when p tends to infinity, one can see that this ratio will tend to this. But it's a bit complicated in a slide to state everything in this way. But it will reduce to this. And of course, as a particular case, but not also the degree of freedom. P and p prime do not need to be the same. So I have some additional freedom between interplaying the roles of p and p prime. That's why if I take, for instance, p and p prime to infinity, of course, I go to this, to our theorem, and we get Ramanujan's result. But you can get another result, like p goes to 0 and p prime goes to infinity, or p goes to infinity and p prime goes to 0, or p and p prime goes to 0 simultaneously. And one of the examples is this: p and p prime go to 0 simultaneously. We get this analog of Ramanujan's formula for zeta 1/2. Of course, p tends to 0 and p prime tends to infinity is another analog, and you can play with this limiting case and always get nice results. For instance, we can get p prime to infinity, say, and keep p arbitrary. Then we get an infinite number of relations for zeta 1/2, for instance. For each p, you get a formula for zeta 1/2. This is a kind of result that you can always get. Another example, I did not record this, but at the end, if you want, I can show the PDF where I have the formula and in the discussion. But there is also an analog. Note that this relation for zeta p prime 1/2 also works for eta p prime 1/2. Why? Due to the functional equation, zeta p prime and eta p prime are the same at this point. So this can also be seen as a transformation formula for eta p prime 1/2. So in the same spirit, one can get an analog of this formula for eta p 1/2 a, the generalization of Hurwitz zeta function that I presented at the beginning. I did not record this because it's also very long as the previous one, even longer because of this parameter a, but I can show at the end. But as one particular example of this formula, when p tends to infinity, p tends to 0, sorry, one can get this formula. Okay, and when a equals 1/2 in particular in this formula, we can get this. This is actually a companion of a formula due to Dixit, Gupta, Kumar, and Maggi, where they actually get something of this with hyperbolic cosine replaced by hyperbolic sine. But we could, with our formula also, when p tends to infinity, recover that formula with the hyperbolic sine. But this is a companion of it with the hyperbolic cosine. And you can get another, like instead of n squared, you can get 2n minus 1 squared when you take p to the 0 and p prime to the infinity in this formula that I didn't show you. But you can always get new relations using this formalism, this general formalism. Again, let me just mention that we have some evidence on how what kind of techniques did Ramanujan use to prove his formula. This is given in a paper by Bernd and Evans. And actually, we have evidence that Ramanujan used this formula to prove his formula for zeta 1/2. Used this formula due to Gleicher. Ramanujan did not know Gleicher's work, but he claimed this formula, and he said that this formula could be used to derive his formula for zeta 1/2. His formula for zeta 1/2 would be a combination of this formula, which contains the right-hand side of Ramanujan's formula for zeta 1/2, with this formula that can be established by Poisson summation formula. So we wondered, okay, for historical reasons, let us try to get this formula in Korsakoff's spirit. Although our proof of Ramanujan's formula in Korsakoff's spirit used the classical theory of Mellin transforms, not the Poisson summation formula that exists actually in Korsakoff theory, let us try to obtain this formula by Gleicher using Korsakoff theory. And you could get this. Again, this function appearing like p squared for every p greater than 0. This formula holds, where f1 is and f2pa is given by this. When p tends to infinity, you believe me, we'll get this formula due to Gleicher. When p tends to 0, again, we get a companion, this formula, which I don't know if it's new, but it's a nice companion of, I cannot track it in the literature, by the way, but it's a nice companion of Gleicher's formula. And we have another neat consequence of that, using Nesterenko's theorem of transcendentality, is that you can get an infinite family of numbers that are transcendental. For instance, we have this corollary. For every p algebraic number, an alpha beta in integers such that they are co-prime, then for every p running over the set of algebraic numbers, this infinite series is always a transcendental number. This comes from this formula. Okay, a is replaced by a rational number. It's like alpha over beta, where alpha and beta are integers. And this guy here, f1p and f2p, are ratios of combination of cosine with exponentials of rational numbers. And using this algebraic independence between pi and e to the pi square root of alpha over beta, where alpha and beta are integers, one can actually check that this series is always a transcendental number by contradiction. It's a consequence of that form. Okay. Sorry, how much time do I have? Because
So you can go up to 4:45. I mean, 14 minutes, maybe 15 minutes more.
Yeah. 15.
Yeah.
Oh, perfect. 15. Okay. So I can. Okay. Thank you. I didn't know. I don't have my telephone with me. I cannot check the time. Sorry. Okay. If I have more 15 minutes, it's okay. So okay. The first formula is achieved, like the Ramanujan's formula for zeta 1/2 is given in Korsakov spirit. Let's move now to the Ramanujan-Korsakov formula. The formula that I gave at the first slide involving the division function. Okay. Alpha and beta are two positive numbers such that alpha beta equals pi squared. And you have this modular relation, where dn is the number of divisions that n has. To seek the correct, or one of the correct analogs of this formula, it is somehow helpful to try to see this as a relation between two double series. Like, let us try write this as a series between two set of integers. It is quite simple to do that, because if I'm counting the number of ways in which n can be written as a product a times b, n is always expressed as a product of two numbers. And when I express n in such a way as that, the dn achieved its goal. The dn may disappear. So it's clear that I can write this infinite series in this way. A double sum, m and n equals 1 to infinity, k0 to mn alpha. Because, okay, mn will be a new variable, n, and then I'm counting now the number of ways in which n can be written as m times n, which is the division function of n. And also the second series can be written this way. So this is completely equivalent. This relation and this are equivalent. But it's actually helpful now to see this as double series. Why? Suppose that we fix one variable of summation, say m equals 1, and take the sum over n. Let us try sum over n, fix n, and try to see how the sum over n works. Okay? If we fix m, say m equals 1, then we need to deal with a series of this type. Korsakov's formula, the Ramanujan-Korsakov's formula, is deeply connected with a series involving this. Okay, k0 to n alpha. And actually, one of the ways to prove Korsakov's formula due to Guinand is actually by seeking a correct formula for this first series. But this was already done 20 years later, 20 years before than Guinand, by Watson, in a paper involving, in which he discussed formally Hankel transforms and self-reciprocal functions with respect to the Hankel transform. But at the beginning of the paper, the only rigorous part of the paper, not completely formal, he proved this amazing formula. Okay, so at first glance, at least from this point of view, if you want to generalize in Koshlyakov spirit this formula, which is equivalent to this, one may try to generalize first in Koshlyakov spirit Watson's formula. There are, of course, again, as I told you, in Koshlyakov's paper, there is one section in which he treats zeta ps or formulas around zeta ps, and another section next when he treats eta ps. And we could do this, and that's why there is this duality. So we can, when we seek an analog of this, we can first try to generalize this part and get a generalization of this part, or start with the right-hand side and try to get a generalization of left-hand side. It's up to us. But in this, actually in the paper, in our preprint on arXiv, we considered both generalizations, like try to generalize this in Korsakov's setting and get a generalization of left-hand side. This is what we call the second analog of Watson's formula. But for the purpose of this presentation, I will only focus on the generalization of the right-hand side and what we can get as a generalization of the right-hand side, okay? So it's quite simple to see how we can generalize this in Korsakov's spirit, right? It's just to replace n by lambda n, and this one by this factor, this rational function, p squared plus lambda n squared over the thing that appears in Korsakov's zeta function. So it's not very difficult to try to guess which will be like the series, the first series on the left-hand side. You get this first series, and it is transformed for every p in this thing. Okay, so let us work with that. Let us work. If we try this generalization, what can we get as the right-hand side? What will be the generalization of this k0, the modified Bessel function of the second kind? And we could get this theorem, this analog of Watson's formula. This formula holds. We get this, which, as I will see below, generalize the left-hand side of Watson's formula, and we get this integral that involves Korsakov's function sigma p plus t over p minus t. One may ask, okay, in this formula of Watson, we get this thing, okay, it is generalized in Korsakov's spirit, but now we have the modified Bessel function. Where is the modified Bessel function here? We have an integral. Where is the k0? What is this a generalization of a k0? And in fact, it is the best. I mean, we could write this in other ways, like combinations of Whittaker function, but in my opinion, this is the best way to present the result because it uses the elementary functions that Korsakoff uses in his manuscript, which is the sigma. But this, as I show below, this is in fact an analog and a generalization of Watson's form. CP1 here is the first analog of Euler's constant given by Korsakoff. This generalizes gamma, the classical gamma in a Riemann sense. Let us see, okay. Let us look at our formulas. So we have Watson's formula, okay? The classical Watson's formula. And then we have our formula. How does this reduce to this when, if this is a correct analog of Watson's formula, this should reduce to this when p tends to infinity, right? It should reduce. It is simple to see that, of course, when p tends to infinity, the left-hand side reduces to the left-hand side of this. Look, CP1 reduces to gamma when p tends to infinity. Log x over 2 reduces, of course, to log x over 2. When p tends to infinity, this guy here reduces to 1. 1 times 1 over 2x is this. Of course, this series reduces to this when p tends to infinity. So we just need to check that this guy here, this integral, reduces to this series of Bessel functions. And the trick for that is just to recall a well-known representation of the Bessel function. The Bessel function as a Laplace transform. When the real part of nu is less than 1/2, the modified Bessel function of the second kind admits this integral representation. In particular, when nu equals to 0, we have this representation. So, okay, let us, so this is somehow related with this integral here. Okay, we have this representation, let us see how we can use it to treat this integral. Okay, when p tends to infinity, we can use the dominated convergence theorem to see that this guy here, this sigma, tends to 1. So this integral here in our generalization will only be 1 over square root y squared plus y dy over, this guy is 1, this sigma is 1, e to the 2 pi to y plus 1 x minus 1. So this. Okay, but now I can treat this guy here, this fraction, as a power series. And then by absolute convergence, this works. I can interchange the orders of the integral and sum and the series, and then get this. But I can recall now the integral representation for k0, this guy, and replace it here. So we get that this integral, when p tends to infinity, when you have the limiting case p tends to infinity, reduced to this series of modified Bessel functions of the second kind. The same trick works otherwise. Like I can replace this k0 by k0 2 pi lambda n x and multiply it by the fraction given by Korsakov. But of course, as you can expect, I won't get on the left-hand side this simple fraction. I'll get another integral representation that in the limit will tend to this, in the same way that this integral representation tends to the series of k0s. Okay? So in fact, it is somehow one of the meaningful analogs that Watson's formula has, this formula of ours. In particular, of course, when p tends to infinity, as I've shown here, our formula reduced to Watson's formula. And when p tends to 0, we can get an analog of it, which is actually due to cover. Is a particular case of a formula due to cover. The first mathematician giving that arrived at a complete Watson's formula, which is related to the Scholler-Selberg formula for Epstein zeta functions. So yeah, we have this. And using now this formalism, bearing in mind the audience that this integral is actually a series, can actually, in the limiting cases, be represented as a series of modified Bessel function, we can now establish the analog of Korsakoff-Ramanujan formula, which is this. Define this generalized Euler's constant as this combination here. And recall the second analog of Euler's constant as this, given at the introduction. Gamma p is this complicated formula that when p tends to infinity reduces to gamma. And Cp2 is the second analog of Euler's constant. Then, using this definition, residual definition of gamma p, which reduces to the classical gamma when p tends to infinity, of course, we get this formula. That generalizes actually, that bearing in mind again, that the Korsakoff-Ramanujan formula can be written as a double series, okay? This is the classical case. Our general formula with general p is explicitly this one. Alpha beta equals pi squared, and we get this, where k0p is again that integral appearing in Watson's formula. Bearing in mind that in p tends to infinity, recall that this will reduce to a series of Bessel functions. And of course, we'll retrieve this from the classical Korsakoff formula. Examples? When p tends to infinity, of course, it's simple to see that gamma p will tend to gamma p is here, will tend to the classical gamma, and we'll get this. When p tends to 0, we get an analog of that. Now with a shifted, like a different kind of division function. I can rewrite this as a meaningful Korsakoff formula with a new division function with these jumps of -1 to the n. But I wrote this as a double series. Okay, and finally, let me recall the entry 3.3.2, which is the transformation formula for the logarithm of Dedekind zeta function. How can we get analogs in Korsakoff series of this? There is an analog due to Dixit and Gupta, where p and p prime are the same. We are going to get an analog by a completely different method when p and p prime are different. And this analog will use the theory that at the first I was trying to seek, of a generalized Epstein zeta function in Korsakoff setting that motivated this work. That was the first question that I asked after seeing Gupta's presentation in OPSFA 16. So again, this has a typo. Remind this is a lambda m, not lambda n. Let us recall the definition of the Epstein zeta functions, or the formal definition of Epstein zeta function that actually works as a double series. Okay, m and n running over the integers, but not simultaneously zero. M equals n equals 0 is omitted from the sum, of course, because this would not make any sense. Why does this make sense? Recall that lambda n by definition is a solution of this transcendental equation, p sine pi y plus y cosine pi y equals 0. But if y is a solution of this transcendental equation, minus y also is. So I can extend the definition of Koshlyakov sequence, lambda n, to the negative integers, defining as lambda minus n as minus lambda n, because it is also a solution of this equation. And of course, y equals 0 is a trivial solution. So I can actually set lambda 0, the first term or the 0 term of Koshlyakov sequence, as 0. So whenever I am m equals 0, I will take lambda m equals 0. I'll get a Koshlyakov zeta function, the term m equals 0. So it makes sense to define as this sum over the integers, because the sequence lambda m and lambda n prime can be extended to the negative integers. So we have this definition. And recall again that in the case where p and p prime tend to infinity, what we get? This thing will tend to 1, this thing will tend to 1, lambda m will be n, lambda n prime will be n. So in this formal notation, when p and p prime tend to infinity, I'll get this, the classical Epstein zeta function. And recall that this Epstein zeta function as a pole at s equals 1 whose residual is given by this. And again, let me recall the previous slides. It has this expansion, the Kronecker limit form. Okay, so we now generalize this with p and p prime being arbitrary. And this is the theorem. We have this zeta function, again, our definition of the Epstein zeta function in Koshlyakov spirit. Like the classical case when p and p prime tend to infinity, this function is analytic everywhere except at s equals 1. Its residue is given by this, the same as in the case infinity, infinity. Moreover, around s equals 1, it has this expansion. This is the generalization of Kronecker's limit formula. This actually will generalize this formula, this. Okay, and using this, we can get a transformation formula for dedicants, for a generalization of dedicant zeta function in Koshlyakov spirit. As an example, for instance, take p prime to infinity and fix p. Then the Epstein zeta function is explicitly given by this. Again, this is an m, not an n. This is a typo. Using the previous theorem, we can get that this has this meromorphic expansion around s equals 1, where sigma, again, is p plus t over p minus t. In particular, you can get when, since p prime tends to infinity, I can get p to the infinity and get the classical Kronecker limit formula. But I can get another analog when p tends to 0 and p prime tends to infinity, which is given by this. Okay? Now, let us finish the talk by giving a generalization of this. Of the entry 3.3.2 of Ramanujan's lost notebook. The generalization is given in the following theorem. If p and p prime are positive real numbers, and sigma prime t are defined by the Koshlyakov auxiliary functions, then we have this transformation formula. In particular, when p and p prime are the same, we get a formula obtained in Dixit and Gupta's paper. The first paper about this formalism of Koshlyakov. But when p and p prime are different, we get new formulas. For instance, tending p prime to infinity and p to 0, we get a formula different than the formula obtained in formalism of the paper by Dixit and Gupta. But how? Let me just give an idea of the proof, how the proof can be obtained. Very simple. Note that in this region of absolute convergence, I can switch the roles of lambda n and lambda n prime because I can reverse. I can sum first over n and then over n. but I can reverse the orders and sum first over n and then over n. So by this, exchanging the roles of p and p prime and lambda m with lambda n prime, I know that this relation always holds. Okay, this is just reversal of orders of summations. But this should hold by analytic continuation. Although this is only proven by a real part of S greater than 1, the region of absolute convergence, this always holds for every S in C. In particular, the expansion for this, the Kronecker limit formula for this, must be the same as the Kronecker limit formula for this. And one can get the Kronecker limit formula for this applying the same formalism as before. But since this holds for every S by analytic continuation, then the constant terms of the Kronecker limit formula for the first epsilon zeta function and for the second must be the same. Hence, we can get the relation because the constant term of this meromorphic expansion is this, and the other constant term was obtained in the previous slide. So equating both and replacing C by alpha squared over pi squared, we can get this relation. So, and finally, we can retrieve the case of Dixit and Gupta when P and P prime tend to 0. Of course, when P and P prime tend to infinity, you get Ramanujan's result. P and P prime tend to 0, we get Dixit and Gupta's result. When P tends to 0, for instance, and P prime tends to infinity, we get another companion, which seems to be new, but it's interesting how this can be derived from a general formalism of Koshlyakov. So it's the end. Thank you so much for bearing with me, and thank you so much for the invitation once more.
Thank you very much, Pedro, for a very nice talk. Are there any questions for him? So, Pedro, I have one question. So, if you see the origin of this theory of Koshlyakov lies in his solution to this problem in heat conduction coming from physics. So, where the P parameter plays a role in maybe the emissivity of the surface or something like that. There is, I don't know much about that. But with your two different parameters, it would be interesting to see what kind of problem does it translate to in physics, as in P and P dash, where both play a role simultaneously. So
yeah, perhaps like this is related like the its conduction in a sphere, right? I think P and P prime would be like did conduction in a crown, like a sphere, the inner sphere, and then the other sphere. I don't know. Perhaps it's related with when P and P prime are the same, the both spheres, radius R1 and R2, would be the same sphere, reducing to Korsakov theory. P and P prime different, perhaps it's like a greater sphere corresponding to P and a smaller sphere inside. And I don't know. I don't know. It's a conjecture. I don't know.
It would be interesting to see. By the way, I liked your proof of proving the generalization of Dedekind-Ita transformation by comparing the coefficients using that C to 1 over C. That's really nice. And plus the Koshlyakov formula, it's very nice to get that explicit thing without losing symmetry. You have that script K 0, if you can go there.
This generalized, right?
Yeah. The best part of this I found was the symmetry is not lost at all. It's perfect symmetric and yeah. So
yes. That's nice. But I think it has to do with the fact that in this I took P equals P prime in this formalism. Like if P is different from P prime, it will be the symmetry could somehow be lost.
Okay, right.
Like in the case P different than P prime in the case of Dedekind's eta function formula. I think that the symmetry will be lost in this case. Like the gamma P will not be so nicely defined. But yes, in this case, it's nice. Like the symmetry is kept. P equals P prime. Yeah.
Right.
Because I could take like P prime here instead of this P a P prime, and instead of this P here a P prime, and these constant terms will be mixed. I think somehow. But perhaps we could get again symmetry, but it won't be so obvious as this.
What is the p tends to 0 case of this? I think you showed.
Yeah, is this.
Oh, okay.
Is this.
The
gamma here will not be so prevalent because because eta p when p tends to 0 has not a pole, right? Eta p, the Korsakoff function eta p when p tends to 0, which is crucial here because in this integral representation, this is actually a eta p appearing because this is the contribution for the Korsakoff secant zeta function. And when p tends to 0, this is like -1 to the k to the s, which has not a pole at s equals 1. That's why the gamma does not show up here.
But the nice thing here is that the gamma, the Euler constant is not there, or not, maybe not nice thing, but I was saying from the point of view of transcendental study, the Euler constant is not there, so the p tends to 0 case is somewhat simpler.
Yes. Yeah. But if you take, for instance, p tends to 0 and p prime tends to infinity, you'll get a gamma coming from p prime tends to infinity because of zeta. But on the other hand, we won't get the gamma again. We only get log of 2 somehow. So you could interchange the several different and try to eliminate, I don't know, to isolate gamma. I don't know. But yeah, in the case, I didn't show this in the paper. We don't have this because it's more complicated. But when you try to prove Korshakov's formula, p and p prime are different. Yes, when p tends to 0 and p prime tends to infinity, or the other way around, p infinity, p prime to 0, you'll get gamma on one side and not gamma on the other.
Yeah. Very nice.
Thank you so much.
Any other questions?
Yeah. Hey, Professor Bishop, I have one question.
Yes, sir.
Hey, Pedro. Congratulations for the wonderful work. It's really nice to see your result. It's really beautiful. We discussed with Professor Dixit previously when you published your paper in archive.
Thank you so much.
Yeah. So I have one observation. Like you proved these formula where you replace like p and p prime, right? Zeta p case.
Yeah.
So in eta p, you also have the factor of like some s comma something, right?
Yes.
S comma 2 pi k. So can't you replace that? Because that thing will give you the analog like this, -1 to the k over m square plus cn square, something like this.
Yes.
So did you consider that case, or it still need to be done? Like, or is it possible? Like, because you initiated this kind of study, so maybe you can tell us if it is possible to study those.
Which formula are you mentioning that I could
so you
consider?
go to the Kronecker limit. Go to the series
Kronecker
you defined.
limit?
Yeah, that's one.
This guy.
Yeah,
this is a particular case.
Yeah, like just go to the one slide before where you define zeta pp prime.
Okay. Yeah. You are asking eta pp prime.
Yeah, means is that analog? Yeah.
Yeah, it's not. There is, but it's very complicated. We did not consider in the paper because it was like in the case of eta p, the coefficient will be like that integral, right? 1 over gamma s, integral from 0 to infinity, that thing. In the case of the Epstein zeta function, it will be like a double integral with mixed terms. But it is possible, but it's since in the eta p case we don't have a Dirichlet series, in the eta p prime case it will be, it is a complication. But yes, one of the motivation, and that's a nice question, is like that eta pp prime is connected with zeta pp prime through a functional equation as well.
Yep.
But we didn't need that explicitly to prove the analogs. But yes, you are absolutely right. There must be, I don't know which kind of analog because I didn't study the analog of Kronecker limit formula, but there is an analog of Epstein zeta function eta pp prime.
Okay.
That connects with zeta pp prime through a functional equation.
Okay, but you didn't prove anything like this, right?
No. With eta
Okay,
p
okay.
prime, no. But I proved with another analog. It's like, as you can see, I mean, let me just show the definition. You have a two-dimensional analog of Korsakoff zeta function. Like in the first sum, the first over m, we have zeta p, and the sum over n, we have zeta p prime.
Yeah.
Right? But we are asking like eta p p prime. Like the first sum is a eta p, and the second sum is eta p prime. In our paper, we consider another analog, which is something of the form. In the first sum, we have a zeta p, and the second sum, we have a eta p prime. It's like a
I
mix.
saw that.
But you're right. If it's eta p, like the first sum, something related with eta p, and the second sum, something related
Is
with eta p
also-
prime, no, because it could be a double integral, like the Korsakoff case. It won't be at all additively serious. The other case, like that we consider, the second analog of Epstein zeta function, it kind of resembles, one can see that it reduces to the classical case. And it has a nice functional equation because you have zeta p, eta p prime. It connects with the Epstein zeta function related with eta p and zeta p prime.
Zeta
You
p
can
prime.
get the symmetry from that. But you are absolutely right. Eta p p prime, no, we didn't consider. We don't plan, I think, to continue that. So that's a very nice point of view to take. But I warn you, it won't be. It will be a very complicated thing.
Yeah.
Like
Yeah.
eta p. Yeah.
That's true. But I always believe in Korsakoff theory because I was working in this theory before. I think if the analog is correctly defined, I think it can be done. Yeah. But you are right. But the way you explain it's correctly right. Yeah. But thank you so much for the talk.
Thank you so much
all
for
the
your
best
talk
for your defense.
2 years ago.
Thank you so much.
Actually.
I remember you as a patient. And all the best for your PhD defense.
Thank you so much.
So, if there are no further questions,
Can you hear me?
oh yeah, do it.
Yeah. So,
Yes.
Hi Pedro. It was
Hello.
wonderful talk. Yeah.
Thank you so
hear me?
much.
Yeah.
Yeah.
No. So I was just wondering, about this Koshlyakov formula which you started with, summation dn k naught. So yeah.
Sorry. Yeah, the
Yeah.
classical case, right?
Yes, the
this-
classical. Yeah, this one.
Yeah.
So, like Ferrer, if I am correct, like Ferrer proved that this transformation formula is equivalent of functional equation of zeta square or functional equation of zeta, you can say.
Yeah.
So, I was wondering that you got a very nice generalization in the case of Koshlyakov zeta function. So, like, do you think or have you tried whether functional equation for Koshlyakov zeta function is equivalent to your transformation formula, what you are getting?
Yes. Yes, but actually, yeah, you're right. This transformation again.
Yes.
This now, as you, sorry, no.
The main one with
this guy here, this guy, right?
So
is actually equivalent not to the functional equation of zeta p squared, but to the functional equation of zeta p times eta p.
Okay, I see.
Which in the case p tends to infinity reduces to zeta squared. But we have this mixture, like zeta p times eta p, not zeta p squared.
This
see. Again, this is very nice. It relates heavily with Rajat Gupta's question. It's like if you have zeta p squared and you start like that, of course, if you start to prove something in this line with zeta p squared, what we'll get? Since it is a Dirichlet series, you will start, of course, with a k0, not this integral. You'll get a k0, the modified Bessel function. And because we can interchange the order of summations, and it is a Dirichlet series, so you'll get p squared plus lambda n squared over p blah, 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 another sum, and you'll get k0. But on the right-hand side, we'll lose the symmetry, because then we'll get to consider an integral which involves eta p squared, not anymore zeta p times eta p. With eta p squared, it's much more difficult to see which kind of analog of the modified Bessel function you can get, because you have a function which is not a Dirichlet series multiplied by t itself.
Okay.
Eta p times eta p.
I see.
So we'll get, again, as I told in the question by Hajat Gupta, we'll get somehow a convolution of things that,
Okay.
of course, will reduce to the modified Bessel function,
Mhm.
but we won't have this symmetry.
Okay.
Yeah, but
I see. I
just to build upon what Vivek was saying, there is another set of equivalence relations for this Koshlikov's formula, one of which is Voronoi summation formula.
Yeah.
You already have the K. If you get the analog, correct analog of Y, perhaps the Y Bessel function, then perhaps you'll have the kernel, and the Voronoi summation would be really nice. Yeah.
Yeah. Actually, the symmetry, this was a very nice question regarding the equivalence, because
Yeah.
why is this symmetric? Because if you
Yeah.
try to write this infinite series as a Mellin integral, you will get, due to the presence of this sigma, like an integral of gamma squared s over 2, zeta ps times eta ps, okay?
Mhm.
But then you use the formal things, like you interchange the line of integration, we get these residues from that, and then you apply the functional equation. But remember, you have zeta p times eta p. By the functional equation, the first zeta p will be transformed into a eta p. But the other eta p will be transformed again into a zeta p. So we have essentially the same. So that's
Yeah.
why appears a k0 and the same guy on the left-hand side and the right-hand side. But if you have zeta p squared, you are in trouble.
Okay. I see.
You are in trouble, not in trouble, of course. I hope that you pursue this
Yeah.
further and you get the analog, but it's more difficult. You'll get a convolution of things.
Mhm. Okay.
Yeah, the
Thank you.
right hand
Thank
side won't be the series then, right? If you convert it to eta p, it won't be converted into Dirichlet series. So you cannot convert into series.
Yeah.
I
I mean,
understood.
you can work. I mean, it's not difficult to work only with eta p, but
Yeah.
with eta p squared, you need to apply some kind of Parseval formula. Try to
That's true.
convert that into a convolution integral. Of course, it will reduce to the Bessel function, but it will be not as so appealing as this formula. That's why we chose and forgot this kind of eta p squared stuff. This was enough for our purpose, and it was nice to get it. So, so yeah.
Thank
Okay.
you.
Thank you for your question.
There are no further questions. Let's thank Pedro